Hello and welcome back to Geology. Today I want to start chapter 16 dealing with groundwater. And we'll see here that groundwater accounts for about 2/3 of Earth's fresh water as a resource used by people. Remember, most of the fresh water is in glaciers, but second most and more readily available to people is groundwater. And one of the key things about groundwater and where it's stored underground in these reservoirs is this idea of porosity and permeability. Think of porosity as the empty spaces or voids between grains. And a primary porosity develops during primary deposition. So those are the initial pore spaces of the rock. Now for secondary porosity, here these are fractures, joints that develop later that allow for conduits or fractures, pore spaces in the rock. Let's think of porosity as water's ability to hold water. Whereas permeability, what I want you to think about permeability is water's ability to conduct water. So this permeability is how easily the water flows through the geologic unit. So you can think of it as a conductivity, the interconnectedness of pore spaces. So sometimes I refer to permeability as water's ability to conduct or transmit the water. So what are some of the factors? So, well, how many conduits are available? How big are the conduits? And how straight the conduits are. You'll see that most groundwater has to travel in these sinuous, curvy, crooked patterns through pore spaces in rock. So permeability or groundwater flow is relatively slow. So we mentioned aquifers. So aquifers are those groundwater reservoirs. A good aquifer is one that's porous and permeable. And there are two types. One is an unconfined aquifer, and this one contains a water table. Whereas a confined aquifer is completely full, and it's confined between two aquitards. So the idea about the aquitard is that it has very low permeability, low porosity, so it's like a barrier to water, to groundwater, and it slows the flow of water. So you can think of it as a aquitard sort of being the opposite of the aquifer. And so if we look at our diagram down here, remember the water table will separate where groundwater exists. So groundwater is in the subsurface. So here's the water table, which separates where groundwater exists. And the other key thing about this groundwater is that we have 100% full pores. In other words, every pore space, every void is full of water. So that's where the groundwater exists. And so we call that the saturated zone. So the saturated zone is this 100% filled pore spaces. And then we see that there's a zone between the ground surface and the water table that's called the vadose zone. Sometimes it's called the unsaturated zone. So here, this is where water will percolate down from the surface, will infiltrate to feed or recharge the groundwater. Now, another thing that we should point out here is because of surface tension, and remember that the pore spaces are really small, groundwater kind of gets sucked up a little bit into these pore spaces, sort of like water will move up a thin straw. And so we call that a capillary fringe. So there'll be a capillary fringe all along the surface here. And note that the water table mimics the shape of topography, and where it intersects the ground surface, it's either adding water to the stream here or adds water to this pond over here, right? And there are also these other water tables called a perched water table. And the perched water table, note that it occurs in the vadose zone, in this unsaturated zone. And so here, this perched water table will have water in it for probably just a few weeks after a rainfall. And you can see that there could be a spring there, but that spring would go dry. We'll talk more about springs in a little bit. And then kind of looking down here is note that below so remember, this would be the unconfined aquifer here, because the unconfined aquifer has the water table. But below, we have two aquitards, which are shale. Shale's fine grain. It's an impermeable, relatively low porosity permeable layer, and so it becomes an aquitard. So there's one here and there's another down here, and so the confined aquifer is completely full and exists between those aquitards. So let's look at groundwater flow. So this is going to flow in response to a pressure differential. So for the unconfined aquifer, groundwater pressure depends on the weight of all the overlying water from that point up to the water table, right? So this would be the aquifer that contains the water table. One thing, that rock pressure doesn't really exert any pressure on the water because remember the grains are interlocking and the juxtaposition of the grains supports the weight of the rock. So remember the water is existing between those grains in the porous spaces. Points at greater depth experience greater pressure. So that's when we talk about this idea of hydraulic head. And imagine we have 2 points, height 1 here on the water table and height 2 here on the water table. And deep down we'll have 2 points, point P and P1 and P2 at the same depth, but note that they're going to be at different heights below these points H1 and H2. So what we see is point P1 here will experience greater pressure than point P2 because there's going to be a greater amount of water pushing down on P1. Now, so this hydraulic head, physicists define it as a potential energy available to drive the flow of a given volume of groundwater, right? So that means that from this point, water here is going to flow out in these directions. It's going to flow out. Usually it flows in curved lines. Now, as a rule, groundwater flows from regions of high hydraulic head to regions of low hydraulic head. So remember, this point H or point P down here is under higher hydraulic head than this point P2 down here. Right, so there's more pressure over here. So water usually will flow from here down in this direction. If we had another point over here, we would see that this will flow off in that direction as well. Right, so that's kind of how we're going to describe groundwater flow. It's going to be in these curved lines. This diagram again, I'm showing the curved line. So flow is in curved concave paths, and the recharge areas are areas where water is infiltrating, percolating down, and feeding water to the saturated zone. It's going through that vadose or unsaturated zone. And then the discharge area is where the water is seeping out, right? So where water would be, so a natural discharge would be like a stream or a spring, or we could discharge water with a well, by pumping it out. Now let's look at this concept of a hydraulic gradient. And so let's imagine we have the water table here, right? 2 points, point H1 and H2. And then the distance or the flow path that water will take is this curved path, and we'll call that distance J. So I've sort of drawn it over here, this distance J. And so the hydraulic gradient would be the pressure differential between these 2 points divided by the distance. And so I've already sort of done that problem down here, right, where I took the height 1 minus height 2, so 20 minus 15. Well, that gives me 5 meters, right? So that's 5, and divided by the distance here, which I have as 8 meters. That's a flow path. So my hydraulic head is 0.63 meters per meter. So in other words, there's 0.63 meters of hydraulic head for every meter traveled along this path. Now, let's keep going here, and there's a little section that talks about the French scientist named Darcy, who sort of figured out groundwater flow, and he was more interested in the volume of groundwater passing a fixed point in the subsurface due to groundwater. So we're going to employ this hydraulic gradient here, H1 minus H2 divided by G, which we had up over here, hydraulic gradient, right? But now Q is going to be some discharge, and the discharge, remember, is going to be some volume. It's either meters cubed per second or cubic feet per second, right? Discharge of volume water passing a fixed point in a unit of time. And A will be that area, that plane upon which the groundwater passes through. And then now we're going to have we need to have some values. And the K value here is conductivity, which is essentially permeability, is how well connected, how big the pore spaces are that allows the water to flow. So and you can look these up in tables. So for coarse sand, the K value, or the conductivity, is about 3 times 10 to the negative 4 meters per second. Whereas for fine sand, it's 2 times 10 to the negative 5 meters per second. So using those numbers, right, I'm going to employ Darcy's law here. Q equals the conductivity times the area, and then times the hydraulic gradient here. And so what we find is that I'm going to use the K value for coarse sand here. And then I'm going to say that the area is 1 meter square. So it's passing through a plane that's 1 meter by 1 meter on the side. And then here's my hydraulic head for the problem that I was using up above over here. So using that, I get a discharge for Darcy's law of 0.00019 meters cubed per second, which is a pretty small value. But remember, groundwater flow is relatively slow. And then if I converted that to feet, it'd be 0.0067 cubic feet per second. So that would be the discharge. And so if you compare discharge of groundwater, usually it's going to be much smaller than that of rivers. And just another way to look at it as well is if we look at the flow of groundwater. So the flow of groundwater is usually about 0.01 to 1.4 meters per day. So that's how fast the water is moving in the subsurface. Whereas in rivers, it can go anywhere from 3 to 30 kilometers per hour, so considerably faster. So anyways, there's not a whole lot of there are not a whole lot of questions on Darcy's law, but I do want you to know this relationship and understand that Darcy figured out how to plot or calculate this discharge of groundwater flow.